All right, questions about things? Yeah, Neil.
I have a question about the programs for the towers of Hanoi.
Yes.
I can write those programs and they work, and I can grind them out, and I understand how they work.
Mm-hmm.
But I can see that they work. But I have no feeling at all why they work. They just seem like a miracle to me that they work. You know, it's like 4 pegs. Well, I just write 4 little words there and send it in, and it prints out these very detailed instructions. You know, so I can't.
Yeah.
Lost as to how to get an understanding of why this recruitment works.
I guess good is the answer. That's why recursion is such a powerful tool, because you can describe such a complicated activity with so many few words. And I guess your question is really not a statement, but a question. Well, how do I get a better sense of what's going on without just being in the forest, you know, tree to tree?
I would do that graph technique. I would say what are all the possible states.
All right,
what's
so
the path I have to go through.
So let me back up and give you a sense of where that problem that I made up, you know, with Fruity Freddy and Ditsy Dotsy, I forget the names I used, but something like that. And they came up with these weird algorithms that don't really work, right? And the idea is that you had four pegs to work with. Let me give you a sense of where this idea came from, because if you see where it comes from, and I have to back up. My thought was that you guys have seen so much recursion in Scheme that when you see a recursive procedure, you'll somehow get the big Gestalt picture. And maybe you do, but maybe you don't. But let me show you where it comes from. And also, if I just wrote intuitively how it works, it wouldn't make sense. So I think writing the specifics is a better way to do the problem. But let me give you a sense of where it comes from. Here's an algorithm for doing towers of Hanoi. We talked about it yesterday. You do the n-1, you move it here, you move the bottom one here, you do the n-1 back. And everybody agreed that worked. Right? So here's another way. Remember I told you it's usually better to cut the problem size in half rather than by 1? You get faster algorithms cutting the problem size in half. It's better to get a recurrence equation that looks like this than one that looks like this. And that's intuitive, because you've knocked the problem size down by a lot more. That's binary search, and that's slower. So the idea is that we're going to do towers of Hanoi, but we're going to do it by cutting the problem in half. So here's the idea. Here's a list of disks, and we're going to take half of them and solve the towers of Hanoi in the top half and move it over here. Okay. And now I'm going to take the bottom half and do the towers of Hanoi in the bottom half and move it over, say, here.
With 3 or with 4 pegs?
What, half of them, whatever that is.
With 3 pegs or with 4 pegs?
Oh, with 4 pegs, presumably. Yes. And then we'll do another half problem, getting this put on top of here. All right, so one of these steps was bogus, and the other 2 were OK. Let's go back and review. Where's my eraser? This chalk is horrible. They shouldn't call it dustless chalk. They should call it rightless chalk. There's just nothing here. Here's a stack of towers of Hanoi. Here's the first step. Take half and do the towers of Hanoi onto another peg. Now let's assume it's just 3 pegs for now, because there you're going to see why it doesn't work right away. With 4 pegs, you might have the illusion that it works, and the reason it doesn't work is a little more subtle with 4 pegs. But with 3 pegs, you're going to see why it doesn't work right away. Take the half and recursively move it over here. Anything wrong with that step? It's a perfectly fine step. The recursion is fine. I'm doing it with half a size. I'm doing it with 3 pegs. This stuff is like nailed down to the bottom, so it doesn't affect anything. The next step, taking this half of a deck and doing recursion on these 3 pegs to get it here, is completely bogus, because I can't use this peg. This peg is dead. That's why I throw the other peg in. Oh, well, now I'm OK. Now I got an extra peg. So you think, now I can do the recursion. But not really, because now this recursive step is really only using 3 pegs. And the first one actually had 4 pegs. So you think to yourself, well, the first one didn't need the 4 pegs. It only really needed 3. So maybe now I can get away with 3. So you write a recursive program to do it. You're not really sure what's going to happen, but you write it. And that's what Fruity Freddy did in the problem set. He wrote it with 4 parameters, with 5 parameters, the number of disks and the 4 pegs. And he's hoping that this idea would work and that he's going to get some nice recurrence equation that looks like this. 3 half problems. And that's going to be a lot faster than the 2 to the n that he got. This would be really fast. This is actually going to end up being n to the log base 2 of 3. So, like between n and n squared.
Yeah, of course.
In 2 days, you'll know why that's true. The point of it is that these algorithms won't work. And they won't work for minor, subtle reasons. And you need to experiment and explore and see why they don't work. And that's really the heart of understanding recursion, is to look at something that looks like it's working. Somebody's trying to do hocus pocus on you, and you figure out why they're trying to pull your leg. And that's the purpose of that question. So how do you really see the big picture? In these questions, it's hard.
I got his to work.
Yeah.
With 4 pegs.
It works with 4, but it doesn't work with bigger sets.
Put in 8, it won't work.
If it works with some small number of disks, but if you try to put in larger ones, you'll start seeing the flaw. So try 8 and you'll see the flaw. Right.
But obviously, if you do it by hand, you can do it. You can move half over and then you can move half over. So you can't get a simple recursive formula that tells you that. That's what you're saying.
You can do this algorithm. You can move this half over using 3 pegs. You can move this half over using the old Towers of Hanoi method, using just 3 pegs. And then you can move this half over using the old Towers of Hanoi method. All right, but that's not a recursive algorithm because you're not writing it in terms of yourself. You're writing it in terms of a different procedure. And you can do that. You're right. Absolutely, Sam. Right.
Isn't the first one be the old Towers of Hanoi procedure as well?
It could be.
It's just that you have that extra pin to be...
To do nothing. Yeah, well, the question is whether... The real question is, does an extra peg help? I mean, if we just do what Sam suggested, then the extra peg really isn't helping at all. We're just going to do 3 problems, each of which is n over 2, and they're going to be 2 to the n over 2 minus 1. You add 3 of those up, and you still have exponential time. I mean, that's at least an algorithm. That would be acceptable, by the way, as an answer to how you use 4 pegs. As long as you analyzed it and told me how many steps it took, it would be acceptable. The question is, what's the best you can do with the extra peg?
Isn't it powers of 3? Yes, 3 log 2n, not n log
3 log 2n and n to the log 2, 3 are identical.
Are they?
Yeah. They're identical. I'll show you this in 2 days also. You saw this 2 months ago, but you forgot. These 2 are identical.
I could win some bar bets.
3 is...
Here's the intuition. This is n to some constant, but this is 3 to a log. And exponents to logs tend to undo themselves and get back to polynomials.
3 is 2 to the log to the base 2 of 3. So you can write the last as 2 to the log 2 of 3 times log 2 of n, and then you can move either direction.
Absolutely, absolutely. I'll review this then. I don't want to review it now, but I'll review it then. I was just in the middle, though. Oh, the extra peg. How much can you use the extra peg? Does it help a little? Does it not help at all? Is it just a complete waste of time? Your gut instinct should be it better help a little, right? It's better. You might even try to make a graph out of this picture. It doesn't end up quite as pretty as the other pretty graph we made. There's no answer to that question that anybody knows, and I didn't ask you that question. I didn't ask you what's the best you can do with 4 pegs, because nobody knows the best you can do with 4 pegs. There is a really good, fancy algorithm that actually deals with a number of pegs in the subproblem. Instead of being half the size, it actually relates to triangle numbers. You could look this up in the Concrete Math book by Knuth if you wanted to see a fancy way of doing it with 4 pegs that cuts the complexity down a lot, but nobody knows that that's the best way.
That's in our book, too.
It's in our book, too, the fancy way? Okay. The triangle number way? Yeah. Right. Nobody knows the answer to this question. And it's a really interesting problem. And one day somebody will know what's the best you can do with 4 pegs, and until then it's just a mystery. This 7 rings problem is a really cool problem. I've mentioned it a million times. And today we're going to solve it. We're going to come up with a number of steps it takes to solve it. We're going to count those number of steps. We're going to relate it to gray codes, relate it to recurrence equations, relate it to induction and recursion. Rather than hold this and fiddle with it as I go, since none of you would ever see what I'm doing, I bought you all a copy of this, and that's why I wanted you to play with it. You're not really going to get it unless you have it in your hand. I sometimes go and give talks about this and try to say, oh, this is really worthwhile to do in class. And I once did it to a group of other professors, and I solved the problem while I was talking and did it and thought that would be really worthwhile. And all they wanted to do was grab it out of my hands. Right? Just give me that thing. And I passed it around the room, and you figure you pass it around the room in an hour talk, and there's 30 people in the room. That's 2 minutes a person, and they're really going to get the idea of playing with this in 2 minutes. They won't. So that's why I bought it for you 2 months ago. So you could play with it and hopefully get some of the gist of it down. Today, rather than hold this, you got another one? I pulled one and you got another?
Everybody can do the sequential move.
Ah, that's right.
With their eyes closed.
We'll pass it to the next person, and then we have, we'll figure out if we have enough people in class to solve the puzzle. I'm going to represent this puzzle this whole day as the piece of steel that you're trying to represent, and there are rings that are locked up around it or not locked up around it. If you've played with this for a while, you'll know that you can get the rings off that piece of steel or the rings are stuck on the piece of steel. And when all the rings are off the piece of steel, that piece of steel comes off the nails, through the rings, and off the whole puzzle. So it starts off like this. 1, 2, 3, 4, 5, 6. That's what it looks like when it starts. And you also notice when you play with this puzzle that one end is easier to take the rings off than the other. Right? There's an easy end and a hard end. So let's call, let's call this the easy end. Call this the hard end. There are two things that you should notice about this puzzle after playing with it for a couple of hours. One thing is that the on-off status of the rightmost ring, that means the easiest ring, can change at any time. You can always take this off and put it back on. That's easy. The other thing you should notice is that there's one other ring whose status can change. And that's it. You have two moves in this puzzle. If you think of a configuration of this puzzle as a list of rings and whether they're on or off, then from one configuration you can move to two other configurations. Now I should mention before I go on, in order to determine what a configuration is, the way I do it is I put all the nails back through the center of the steel and I look at the rings and I see if the rings are around the steel or not around the steel. All right? Everybody's got a different way of holding it, and sometimes people pull the nails out. In order to determine which configuration you're in, you really have to have the nails kind of through there and see whether the rings are around it or hanging below or above. If they're hanging below or above, they're off. If they're around it and intertwined, they're on. And that's what I mean by a configuration. Some of the configurations that you think are different might all really be the same, is what I'm saying. Okay? So one thing you can do is move to a configuration where this toggles from being on to off. You can always do that. Another thing you can do is the following. From now on, instead of making this picture, I'm going to put a 1 underneath each spot if the ring is on, and a 0 under the spot if the ring is off. So we're back to binary numbers. So it starts like this. And one thing you can do is turn it into this. Okay? The other thing you can do from this position, which other one can you take off from this position? Anybody know? The second from the right. You can also go here. I want to generalize this to any possible configuration. I want you to realize exactly, given a configuration, which two places you can go. And I want us to all agree on this before we do anything else, because those two things are important to see. Let's pick an arbitrary configuration in this game. 1, 2, 3, 4, 5, 6. Something like this. 1, 0, 1, 1, 0, 1. Let's see. Here, Blake, what's one position I can get to? Pick the easy one. This right one can change. So?
1, 0, 1, 1, 0, 0.
Right. I can change that right one, so that's one position. What's another position I can get to? Now here we have to think a little bit. Does anybody know? 1, 0, 1, 1, 1, 1. How do you know what the two are? Let's make sure we all know what these two are, and I'm going to completely describe it rigorously. You could write a program to determine this. Here's what you do. You start on the right end, and you look past all the zeros that you find until you hit the first one. In this case, there are no zeros at the right end, so you hit a 1 right away. the position to the left of that first one that you hit can be switched. That's the fundamental mechanical nature of this puzzle. That the second to last one off the right, after the first one, can be switched. Let's look at it here. The second to last one can be switched. The second one can be switched. Here's another example. 1, 2, 3, 4, 5, 6. Well, for sure we can switch this one. That we can always do. 1, 0, 0, 1, 0, 1. What's the other one we switch? Let's do it together. Run through the zeros until you find the first one. The position to the left of that can be switched. 1, 0, 1, 1, 0, 0. These are the two positions you can get to from here. Are there questions about this so far? This is completely rigorous. There's no choice as to what the two positions are. One is obvious, and one you have to do a little bit of a calculation. The way a computer scientist would write this down is they'd say, look for the following pattern on the right end. 0, star, 1. 0 star means 0 as many times as you want, including 0 times. Either no zeros or as many zeros as you want. Keep looking for that pattern until you see a 1, and then it's this position here that can be toggled. All right? This is sometimes called a regular expression. It's just the way you describe patterns of things. You'll see it in web designing programs looking for patterns. If you go to Barnes & Nobles and want to look up a book and see what its price is, you look for a match, looking for your book, and then look for the price and you pull it out. These are used in a lot of places. They're used in theory of computation, used in text editors. These come up a lot. You should have that notation down. 1 0 star means one with lots of zeros, even no zeros. And that's a way of describing what patterns we can get to one from another. So let me stop here. Questions so far? All right. Knowing these two things is enough to completely solve this puzzle, but we have to flush it out. Who thinks they can figure out the two positions to move to from any one position? Everybody think so? Who wants to volunteer that they don't know how so I can call on them and teach them? Here's a 7-ring puzzle. All right, who doesn't mind when I pick on them? Heather, you're always polite. Give me the two things that this can turn into.
1, 0, 1, 1, 0, 0, 1.
Okay, that's one. Oh, that's the easy part, so you're off the hook. Make Mike do the next part.
1, 0, 0. That's the trick. 1, 0, 0.
Good, very good. Okay, these two things. Okay, again, look, 0 star, here's the first one. That guy can toggle its state. And it's built that way. And you can build other puzzles that have this property, and they would be isomorphic to this puzzle. They would look different, but they would have the same properties. Here's our beginning position again. The first thing I'm going to do is not talk about gray codes and binary things, because that I'll do at the end. I'll do that the second half. I want to do the more interesting part first, the recursive part first. I should just remind you, though, that if we made a picture of the graph of this game, it would be a straight line. It would be an uninteresting graph. And if you actually were just really careful to note what configuration you were in, you could solve this puzzle by starting at this point, ending at this point, and following the straight line. And a lot of you did solve it that way, without thinking recursively at all. All right. It depends what your background is. When I finally solved this puzzle, I figured out a recursive idea, and I did it like Neil was saying. How did I saw the big picture, and when I actually did it, I just ran the recursive idea through my recursive interpreter in my head. And I had no idea where I was up to. If I got lost, like what the bindings of the variables were in the middle, I didn't realize that I was really on a straight line. I was just lost. I would have to start all over again. So when you do it recursively, you might not see that it's really just a straight line you're traveling down, but you are. But let's think about this recursively. Here's what we're going to do. This is the easy side, remember, and this is the hard side. And we'd like to take off all these rings. And as many of you discover, and I think a lot of you do discover this, that what you really want to do is work really, really hard and get this guy off. Because once this guy is off, you can virtually just chop. If you had a big shearing scissors, you could chop this piece off the puzzle, and you would just have a new puzzle that has 5 rings in it. Once you get the hard one off, it doesn't come into the picture at all. It never interferes with anything. It just hangs there. It's like that 7th ring that you hang it up on the wall from. Okay, it doesn't do anything. So what we'd like to do is step by step, this is a lot of steps, dot, 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 get to here, and then the next step, dot, 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 would be to get to here, dot, 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 get to here, etc. One by one, through a series of steps, take the rings off from the hardest down to the easiest. That's what we'd like to be able to do. But there's a lot of work to get from here to here. Now, why am I writing it this way? Because this is a recursive way of doing it. It's also an iterative way of doing it. But it's a simple recursion. What I'm going to do is I'm going to show you how to get the hardest ring in a puzzle off. And then I'm going to solve the puzzle for n minus 1. Let's write that down. I'll call it Chinese ring n. Get the hardest ring off, and then Chinese ring n minus 1. You believe that? If you played with the puzzle, you should believe that. Get the hardest ring off, and then you got the same puzzle with one less ring. If you took the right ring off, you don't have the same puzzle with one less ring. Okay, you got a very hard puzzle that's not too much easier than the original 6-ring puzzle. It's taking it off the left end that really gives you a puzzle exactly the same as the one you started with, except with one less ring. When this is off, these don't get affected by it at all. When this is off, this is not like a 5-ring puzzle. It's very complicated, much more like a 6-ring puzzle. So here's our recursion. The question is, how do we get the hardest ring off? Well, you guys know how to get the hardest ring off because you know how to change to this state. You know the 2 binary numbers that sit around here. Well, let's figure out what they are. One of them is this one. What's the other one? Zero, zero, one, 0, 1, 1, 1. 0, 1. Oh, is that helpful? Are we just going to like look at it and get nowhere?
You can turn the first one as your
You can come up with all sorts of ideas, but we need a nice recursive idea. Something that's a big picture, something that doesn't look down at the details here. So now let's concentrate just on that. This looks like a dead-end possibility. We're backing up. I don't think this is going to help us get a recursive idea. And if you think it might take a day until you convince yourselves that maybe it wouldn't. But it's not going to. So let's concentrate on something that will help us. We want to go from here to here. If I want to pull this off, what should this be right before I pull it off? That looks better. Too many zeros? Thanks. 1, 1, 0, 0, 0, 0. If I get it to look like this, then the next thing I can do is take this off, right? That's the real one. I wrote the wrong one before, and that's the real one that goes before this. But this should give you a hint. How do I get it to look like this? All I got to do is leave these where they are in the puzzle, ignore them completely, and solve the puzzle for 4 rings. Okay? If I do that, then I take one step to turn it into this. Not quite into this, right? What does it look like? 0, 1. When we looked at the one right before this, it wasn't what we wanted. When we concentrate on just getting this off, we get something that still isn't what we want. But we can fix it. So let me back up. In order to get this hardest one off, we have to make it look like this. Then we take the hardest one off. But now we want to make it look like this. So what do? You put them back on. Let me review this. If you want to pull the hardest one off, take n minus 2, or 4 rings, and take them off the puzzle. Then take your hardest one off, as you're allowed to do. Then put those 4 back on the puzzle, and you're up to the stage that we want to be. Let me write this down. I'm going to say how to get the hardest ring off. Chinese rings, n minus 2. Slide off hardest ring. And how do we get to here? Reverse Chinese rings, n minus 2. This is the hard part when you do it in your head, because this actually is going from an empty off ring situation to an on ring situation. So you have to kind of do it backwards in your head. You do the Chinese ring n minus 2, but then you reverse the order of how you do things. That's the part that's hard to do recursively in your head and why it's so easy to lose track of where you're up to. Because remember, each of these recursions is calling other recursions, and some of them are forward and some of them are backward, and it's just like, how do you remember? You get good at it and you practice and you can remember. Let's analyze this. This is going to solve the problem. It's really elegant. I mean, you could write a program to do this. You could write it in Scheme. It is 6 lines long, and it will tell you which position to move to. And it'll generate these configurations. And it's magic, like Neil said before, because all the hard stuff is done behind the scenes. The big picture is the relationship that's going on here, the recursive relationship. But what I want to do now is switch gears. I want to analyze how many steps this takes now that we know exactly the algorithm. Let me stop. Questions about the algorithm? Yeah, Todd.
You know, in Towers of Night, we keep changing the target from to using for reverse Chinese rings. Would you change the operation, saying that what used to be a 1 bit is now means the same as a 0 bit?
That would be fine. If you put an extra parameter in that says, you know, what's on and off, then you would toggle that bit.
So you could use the same algorithm.
Absolutely. You could use the same thing and put an extra parameter in. Or you could just write a helper function that runs the old algorithm and just reverses its order, which would also be the same. It would be equivalent. You could do either one.
Position, you have only two moves.
That's true.
So you can program it to say whatever you came in on, you can't go out on.
Agreed. Right. Right. Instead of a recursive routine, you could also just say, check where you just came from and do the other one. And you could write an iterative program for this. Absolutely. And in fact, you're going to have to write a program for that in one of the problem sets, or the equivalent of that. Let's analyze this. Who can give me the recurrence equation for this? How much time it takes? EJ, can you do it? You're rubbing your beard. You look thoughtful. The time it takes to do the Chinese ring problem. Let's split it up into pieces. How much time does this take? That's a recursive call. Tn minus 2. Good. We got 2 of those. So I'll make it 2Tn minus 2. What else? We have this line, slide off the hardest ring. That takes 1. I'll put that at the end. And what else? Good. That's the recurrence equation. That's the exact recurrence equation for this puzzle. And you know that it's the only solution possible, so it's the fastest. You're not going backwards here. This is a completely straightforward solution. We need a base case. In fact, how many base cases do we need? 2 base cases, because this depends on 2 smaller values. So we need a base case for the 1-ring puzzle and a base case for a 2-ring puzzle. How long does it take to solve a 1-ring puzzle? 1 step, pull off the ring. How long does it take to solve a 2-ring puzzle?
2 steps.
You take the left one. I don't think 3. I think you can change it to this, and then you can change it to this. Okay, so I think it's 2. That's our recurrence equation. We're going to spend the next half hour or so looking at this and trying to solve it. Right now, the only technique you have for solving recurrence equations, and it's not a bad technique at that, is repeated substitution and looking at the sum and hoping to God you can do something with the sum. Right? That's not a bad idea. But there are 3 or 4 other methods that we'll get to tomorrow and the day after. And we'll continue with that idea of studying methods for solving recurrence equations. But now I want to try the only method that we have and see where it gets us. And it's not going to get us anywhere. It's going to be ugly. And anybody who's smart enough to see how to fix that method, don't volunteer to show me now. I want to pretend that we're really at a dead end. There is actually a way to fix it, but we're not going to fix it. we're just going to be at a dead end. But I want you to at least understand why it's a bad way to go, or why it looks like a bad way to go. Here's our method. Our method is to get rid of the Tn minus 2 and get rid of the Tn minus 1 by reusing this formula and substituting in. So let's do it piece by piece. Let's start with Tn minus 1. Tn minus 1 equals 2Tn minus 3 plus Tn minus 2 plus 1. And let's put it back in there and see what we get. Tn equals, who can do it? 2Tn minus 2 plus Tn minus 2 gives 3Tn minus 2 plus 2Tn minus 3 plus, we're taking this and putting it in there. Plus 2, good. You feel good about this? We can continue now. We could do 3Tn minus 2 here and do another substitution. But it looks like things are just getting ugly. For one thing, I have no idea really what these numbers are turning into. I don't see a pattern. Oh, maybe it's the Fibonacci numbers. No, it's not. But it would be cool if it were. And what's going on here? Am I going to get like Tn minus 4 the next time? I mean, I'm trying to get rid of these things, and it looks like they're growing. We could do another step. We could do a few more steps. But we would start to give up. This isn't so helpful. So at this point, you come see me in my cubicle, or you give up and you just go on to another problem. Or, and this is what you should always do, I don't have a clue how to do it with my power method, so let me see what the answers are at least.
One, 2, 5, 10, 21, 42, 85.
Hike. Let's do it. First two are the base case. Okay, so how do you get T3? T3 is defined through this recurrence, right? T3 is 2 times T1 plus T2 plus 1. That's 2 times 1 plus 2 plus 1, which is 2 plus 2 plus 1 is 5. Now do the next one. It's going to be 2 times the 1, 2 before it, plus 1 times this. So 2 times 2 is 4, plus 5, plus 10. 2 times the 1 twice before, 10 plus 10 plus 1. All right. What's the next one? Not Sam. Somebody else. Didn't take that long. 42, 42, 85. One more. 1. Now, let's look at this table and see if we can find a pattern. This isn't like I wrote down some bizarre sequence of numbers. There's a lot of patterns here. It doesn't take a genius to see some kind of pattern here. Something's going on that we can write down. So let's write down what it is, even if we don't have a clue as to how to solve this recurrence equation. What we're going to write down is something that we will have a clue how to solve, and that's going to actually give us a solution to the whole thing. Which is very pretty, yes. What relationship do we see here? It doubles.
If there's an odd, it doubles. If it's an even, it doubles plus 1.
I heard it about 8 times. Good. If the number's an even number, it gets doubled and get 1 added to it. If the number's an odd number, it just doubles. Maybe that's just coincidence, and the next number that won't work for.
Oh, no, it will.
It really does. How do you know when you just see something that's coincidence and when you don't? There's a famous function. I think it's this one. I don't remember exactly. Is it this one or this one? Is it this one? That it gets you prime numbers?
Yeah, there's a 41, but I'm not sure whether the 41 is.
And I'm not sure if it's plus or minus. There's a function that if you put numbers in, the first 40 numbers you put in, you get prime numbers. And the 41st number you put in, you don't get a prime number. I don't know if it's this or not, but I could figure out which one. And the 41st number, you can factor it, so it's clearly not a prime number. But if you're the kind of person that just tries, say, 10, and that's a good enough sign, then you'll say, well, there's a formula that generates prime numbers. But it's not. So we have no guarantee that this pattern is going to continue. We have every right to conjecture, as curious, skeptical people, that it's true, but we're going to have to prove it's true. Right? And how do you know when you've really discovered something that's true and you can prove it and something that's just a red herring? Well, you never know. And you get better and better at it the more of these you do. So here's our conjecture as you've all said it. T of n equals 2Tn minus 1 plus 1 when n is even or odd?
When n is odd.
When n is odd. And when n is even, T of n equals... No, I think we did it backwards, huh? I think this n should be even.
Your chart sort of sloping.
Now, what's sloping?
Think bottom of your chart, here.
You're saying that if n is even, you get an odd number, and that's not the case. You had it right there the first time. You're saying if n is even, you're going to have an odd number.
Let's check it. If n is even,
You have an
then I double the previous one. If n is even, I double the previous one. And that's all I do.
So that's going to be an odd.
I want to erase the minimum number of sums. We had it right to begin with. You were all right to begin with. Sorry I switched it on you. Let's double check that it's true. If n is 6, it's going to be twice the number before exactly. And if n is, say, 7, it's going to be twice the number before plus 1. All right, let's look at this conjecture. The only thing we know is this. This for sure is true, right? This is not a conjecture. This is golden truth. This is a conjecture about the same T of n. We're going to prove this conjecture is true by induction. Not because you have to prove it by induction, but because I want you guys to understand induction, and this is a natural inductive proof, and it's really easy to prove this by induction. And sometimes the easiest inductive proofs are the ones that you scratch your head on the most and say, I don't get it, and those are the good ones to practice. So if we're going to prove this by induction, this is the first time you've actually gotten kind of like a double-edged sword with the induction, in the sense that we got a lot to prove here. We got an even case and an odd case. And you'll say, do I have to do those separately? Well, the good thing about induction is that you can prove anything by induction. If you want to prove more, you get more in your assumption. So you can throw more into what you want to prove as long as the assumption to what you want to prove still works, as long as that last connection still works. Sometimes the easiest way to prove something actually is to prove something harder, because what you gain in the assumption is more than what you have to end up proving in the conclusion. So ironically, with induction, you can sometimes prove harder things more easily than easy things. You can. So here we're going to take this all as one thing that we want to prove. And we're going to take this induction assumption that this works for anything smaller than n. I'm going to write down what we know then. We can assume by induction that T of n minus 1 equals 2Tn minus 2. And that's when the case when n minus 1 is even. And when n minus 1 is odd, we know by induction assumption that it's 2Tn minus 2 plus 1. This is what I can use as an assumption. This is what I have as my golden truth. And I want to get to this. Okay, that's our plan. I want to start here, get to here, use that if I need to. Questions so far?
Show base cases?
We'll worry about the base case later. We should have to show a base case. You can show a base case by checking, by the way. Right? I mean, you can just check. You can do it. It's not a hard thing. We can do it at the end. OK, so here's what we know. I'm going to write this golden truth over here, copy it down. Tn equals Tn minus 1 plus 2Tn minus 2 plus 1. And I need to show that these two things are going to be true. One case n even, one case n odd. So let me consider the case where n is even first. I want to get from here to here. I can use these assumptions. How do I do it? Plug in what? I want this to turn into that. I got Tn minus 1 here. So wouldn't it be great if I could just get rid of this and substitute it with another? Tn minus 1? I can, look. If n is even, what's n minus 1? Odd. That means this is true. Everyone agree? Because that's a smaller case. So instead of Tn minus 2 times 2 plus 1 that you see over there, I can replace it with this. That equals 2Tn minus 1 for the case n even. I got that first part. This is one step. This isn't a long, hairy proof. This is induction at its best. It's the slickest proof in the world. Boom, boom, boom. We're done. All right. Now before I go on to the next case, and the people who are making curlicue faces with their eyes and nose, I want to make sure you're still with me. We have this as truth. We have this as an assumption. We're trying to prove this. In order to prove this, I try to do it in cases. I said the first case, n is even. So I write down my truth again, and I notice that if n is even, n minus 1 is odd. And if n minus 1 is odd, I can use this step for my induction assumption. And in place of 2Tn minus 2 plus 1, I can rewrite Tn minus 1. And that gives me 2Tn minus 1 QED divided by 2. That means I'm half done with my proof. N odd now. All right, if n is odd, you start with the same exact truth. This is truth is true for any n, even or odd. So we start with the same thing. It equals Tn minus 1 plus 2Tn minus 2 plus 1. Now, if n is odd, n minus 1 is?
Not odd.
Not odd. It's even. So we can use this as our assumption. So instead of 2Tn minus 2, we can rewrite Tn minus 1. But this time the plus 1 stays there because we were using this. And what do we get? 2Tn minus 1 plus 1. QED. We started with this assumption. We used our truth. We got the next case. To show that this really works, you got to show that it's true for T of, say, 2 and T of 3. You can start for smaller cases. And you can check it's true.
T of 1 and T of 2 doesn't work?
Because we don't have a T of 0. So if you want to show that this is true, you just have to show that it's true for T of 2 and T of 3, right? Those are the lowest cases that this means something for. And you can check it works for T of 2 and T of 3. All right. So like, I bang induction over your heads, and I tell you how important it is. And maybe you could have come up with a proof for these things without induction. But if you get good at induction, it's just so slick and so easy that if you read a paper by somebody, you know what they'd say? They'd say, by inspection you can see these properties, and it's an easy inductive proof that this is true, period. And then they're on to the next paragraph. And in that little sentence is 20 minutes of talking right now. All right? But that's the assumption people will have when they're writing things like this down to a broader audience. All right, questions about this? So now we've got that this is true, and now we're ready to move on to the next step and try to actually get a formula for T of n. We still got a long way to go. We've still not solved anything. We've just convinced ourselves that this is true, and we've gotten out of the horrible world of this more complicated recurrence equation. And it turns out that the easiest way to write the final formula down is to separate the cases. To say that if you have an even number of disks, it takes this many steps, and if you have an odd number of disks, it takes this many steps. And if you try to combine them into one formula, you can do it, but the formula looks so ugly and unpleasant that any mathematician would never do it. They would just say, n odd, here's the case, n even, here's the case. And that's an aesthetic judgment. But you could always compose two functions into one uglier one with -1 to the n's and all sorts of weird things like that. Let's work with this. Now that we've got the double n minus 2 and n minus 1 out of there, and we're down to just n minus 1, things look good. But let's think about what happens here. When we did these repeated substitutions before, the pattern started to repeat. Why? Because we did the same thing every single time. Look what happens here when you do repeated substitution. The first time you double the previous one, but then it's an odd number. So the second time you got to double it and then add 1. And then you got to go back and double it. So you might not notice the pattern. So what we're going to do is try to get it to a point where we can just use the same thing repeated all the time. And what I mean by that is the following. We're going to run this substitution through so that t of n for even numbers depends on t of n for other even numbers, and t of n for odd numbers depends on t of n for other odd numbers. So the same thing happens every time through. So we don't have to shift back and forth between these two repeated substitutions. Sam doesn't like this idea.
No, I do. It doesn't.
Maybe even do this at your seats. Sam, I know you've already done it at your seat. So let's go ahead and run this through once. T of n equals 2tn minus 1. What happens when you try to substitute for tn minus 1? Here's tn minus 1. If we're going to start with this, then tn minus 1 uses which recursion? Uses the second one. So tn minus 1 will be 2tn minus 2 plus 1. Take it back in here. What do you get? 4tn minus 2 plus 2. That's when n is even. Here's what I did for those of you who didn't follow that last step. I just took this as a starting point, and I substituted for tn minus 1 by using the second one, because it switched from even to odd. So I took 2tn minus 2 plus 1 and put it in place of here. And I got 4tn minus 2 plus 2. This is much better, because now even numbers depend on other even numbers. And now the pattern just repeats itself over and over. So I'm going to write that down. 4tn minus 2 plus 2 when n is even. And who can tell me the appropriate one when n is odd? Sam, you can tell me.
Oh, goodness.
I knew you weren't ready. Oh, quick, somebody beat him. Somebody beat him.
4tn minus 2 plus 1. It's either plus 1 or plus 3.
Think it's the same? Well, let's do it. If there's an argument, we must do it.
No, it has to be an odd number.
Let's try. If we start with here, 2n equal 2tn minus 1 plus 1, and then we substitute for tn minus 1 using this, then in place of here comes in 2tn minus 2. That's 4tn minus 2 plus 1 at the end. You get these two formulas by doing one repeated iteration, either this into this or this into this, depending on whether you start with odd or depending on whether you start with even. And these two recurrence equations are true as long as these are true. And now we're going to work with these. And this is what's going to give us a sum. We're going to get more practice doing sums. We're going to get an actual answer. And we'll figure out how many steps it really takes you to solve this 6-ring puzzle, and how many steps it takes you to solve a 10-ring puzzle, and things like that. Who's still with me? Nobody?
I see the mechanics of what you've just done, but I don't understand why it's better for evens to depend on an even.
Oh, because then we can just keep using this one rather than go back and forth. And I guess I can't, look, it might not be better. Maybe you would have noticed the pattern by going back and forth repeatedly, and we could have just had one formula. But I don't think you would have noticed the pattern so easily. I think if you repeat the same recurrence equation over and over again in the substitution, you have a much better chance of noticing the pattern. In fact, this looks an awful lot like the Towers of Hanoi recurrence equation. Instead of 2tn minus 1, we have 4tn minus 2. So if we could do that one, we'll be able to do this one. The thing is, John, that evens depend on evens. So when I get a tn minus 2 and I want to substitute for that, which one of these do I use? I use this one again. And that'll become tn minus 4, so I use this one again. That's the key thing, that I stay in the same line. So you're asking yourself, well, how would I have known to do that? You know what you would have done? You would have gone back and forth here to get one long formula. It would have been just as ugly as you started, and you would have come to me, and I would have given you a hint. What if it's a good idea if we can get even to even? And you would have thought of this. Or you would have maybe discovered it by yourselves, too. We do each of these separately. So this board will be the even board. Even board. This board will be the odd board. All right. We want to get rid of this n minus 2. The tn minus 2 there stinks. We want just n's on that side. No capital T's. No capital T's on the right side. We want a formula for n. So to get rid of the capital T, we write down what it means. Tn minus 2 equals... Andrew Hall, good morning. Can you tell me? Yeah, I never give you a good morning. Here's your good morning. What does tn minus 2 equal? Run it through that formula. Processing, processing. N minus 2 goes in there.
Minus 2, wait,
Put an N minus 2 right into here.
okay.
What do you got?
So 4t n minus 4
Good.
plus 2.
Good. Super. What's next? What's next? The next step is to get rid of this Tn minus 2. That's what we're trying to do. We're going to get rid of it. So we're going to put this in its place. Here's what we get. Tn equals 4. And in place of Tn minus 2, I'm going to put big brackets. 4Tn minus 4 plus 2 plus 2. Get it? Okay. All right, so Peter, help me multiply this out and see if we can look for patterns. What do I get here? 4 squared plus 2 times 4 plus 2. Good. Now, if you're inexperienced with this stuff, you're not likely to see the pattern yet. But when you get more experience, you are likely to see the pattern. You'd have to do it maybe 1 or 2 more times if you're just really learning this stuff to see the pattern. But try to get a sense of what's happening. I just did it twice. I got an exponent of 2 here. That's an easy pattern to notice. I did it twice, and I got 2 plus 2 times 4. What's going to happen next time? Maybe you see it, maybe you don't. Let me help you. Next time, all this stuff is going to get multiplied by 4. So the 2 here is going to become 2 times 4. The 2 times 4 here is going to become 2 times 4 squared. And then we got an extra 2 that we add on at the end. So this will end up having just what it is now, except with a 2 times 4 squared extra term. What happens is we're getting a geometric series there, 1, 4, 4 squared, with a 2 in front of each piece. Let me show you what it would look like if we did it again. T of n, 4 cubed, Tn minus what? Minus 6. Anybody mind if I write 3 times 2? We did it 3 times. We took 2 away. It's easier to write it that way because when we do it r times, this is going to be r times 2. Right?
Plus 32 plus 8.
Right. Don't write it that way. Plus 2 times 4 plus 2 times 4 squared. I changed the order here so you could see it in ascending order. That's what would happen if you did it 3 times. And now, if you could always do this brute force, not just guess. If you're not sure, do it. Multiply it out, see what happens. Don't simplify it like Sam was kind of kidding before. I think he was kidding. Don't simplify it. Leave it in this pattern so you notice the pattern. There's no great goal to square it out and say, oh, I got the number, like my 6th grade students would do. That's what they do right away, and they'd be really proud because for them, multiplication and addition is challenging. So for them, the goal is to add this as fast as possible and get the right answer. And the real goal is to see the pattern.
In that case, do it 2, 2 cubed, 2 to the 5th. That will show the pattern more clearly. 2 plus 2 cubed plus 2 to the 5th.
Right, and would make it harder to sum later, perhaps. But, oh, maybe not. You could do that. We could do that. Let's do this r times. 4 to the r, Tn minus 2r, plus, and here's the sum, 2. I'm going to factor out the 2 if nobody minds, because there's a 2 in every term. 1 plus 4 squared. What's the last term? 4 to the r minus 1. 1 less than the number of times we've done it. Right? This is 4 cubed. We get up to squared. That's very common that you get 1 off there. In fact, what you're likely to notice in doing these kind of substitutions is that similar things happen every time. And you might wonder, and sometimes students ask me this, well, why don't we just do it for some general formula and see what happens and summarize all our results? And that's just what some mathematician did, and that's called the master theorem. And it summarizes just what complexity you get if you do this with some general kind of formula and you see what happens. You'll notice when you do this, you get 2 pieces. This sum piece, right? And this piece here that sometimes disappears and sometimes turns into something. Sometimes this is going to be the major part of your complexity. Sometimes this is. Sometimes they're the same. The master theorem basically looks at the function in advance and looks at these different numbers and tells you whether this is the main piece or that's the main piece. And it only works for certain recurrence equations. It actually doesn't work for this one. You'd have to do this one plain. You can't use the master theorem for this one. The master theorem works for equations that come out of polynomial time algorithms, equations where you're dividing, where you divide and conquer rather than subtract and conquer. So the master theorem will give you answers so you don't ever have to do sums for those kind of recurrence equations. But there are some you'll have to do sums for, so keep your skills sharp. Here's what we're up to. There's two pieces. We still want to get rid of this t, and the way to get rid of it is we have to go ahead and ask ourselves, what's the base case for n even? What is it? N equals 2, right? N equals 2 is the smallest one. And t of 2 equals what? 2. That's our base case. So we'd like this number here to turn into a 2, and we're going to make r as big as we need to have it be in order to have this turn into a 2. Forget the odd board. We're taking both boards. We want n minus 2r to turn into a 2. What should r be then?
N minus 2.
Just curious, is it 0 even?
Yeah, but there's, I guess we could say t of 0 equals 0.
Right.
We could do that. I didn't use that as the base case, and that would work just as well. I just didn't do it. And this will work just as well, too. So let's stick with this. But you're right, Doug. I could have used t of 0 equals 0. But I never even used that as a base case. I assume there are no puzzles with 0 rings because they wouldn't sell for a lot. Oh, wait, here's another one. Here, I'll give you it for $10. I'm going to buy the whole world one of those. Oh, yeah, I guess the bar costs money. Remove the bar. All right, let's do this. Why are we doing this many? We want this t, Peter, to disappear. The way it disappears is when the inside of the function here, where the parameter becomes 2. So I can substitute t of 2 for 2. And you got it? So we just got to make r equal n minus 2 over 2, and that'll make that disappear. So here's what we got. T of n equals 4 to the n minus 2 over 2, 4 to the r, times, what's this going to be? It's going to be 2. T of 2 is 2, so times 2, plus, now let's do the formula. Anybody remember how to add up this formula? Oh, it's a mess.
4 to the r minus 1 over 3.
4 to the r
Minus 1. 4 to the r minus 1.
Good. That's a geometric series. Remember, you go up to the next exponent, you subtract off that 1, and you divide by 4 minus 1. All right, let's do it. Here, we're going to do this together. We're going to do this piece together. X equal 1 plus 4 squared up to 4 r minus 1. What do you multiply both sides by?
1 minus 4 to the r.
We're doing our trick. We multiply both sides by 4. So that shifts everything down to 4 squared, 4 to the r minus 1, and 4 to the r. Then you subtract. You got 4 to the r minus 1 equals 3x. So x, our original formula, equals 4 to the r minus 1 divided by 3. That's the general way you do any geometric series. We did it last time. It always works. It's a good trick. And it works for things that aren't even geometric series. If I put the numbers 1, 2, 3, 4, 5 in front of these numbers, it would work also, right? But we'd have to do it how many times? We have to do it twice. Right? So you can do any kind of weird series with this trick as long as there's some nice order to it. Right, that's review, and I was going to skip it, but I'm glad I didn't, I suppose, since too many looks of confusion. Now we've got this, but we have to plug in something for r. It's got to be n minus 2 over 2. Well, look, we got this nice answer now for n even, but what a mess. Can we simplify it? We can simplify it a lot. If you have a number here, 4 to the n minus 2 divided by 2, What is that the same as? It's 4 to the n minus 2 times 4 to the 1/2. What's 4 to the 1/2? Square root of 4 is 2. Right? So what this really is, this piece here is really equal to 2 times 4 to the n minus 2. Okay? That piece here,
No, that's not right.
no?
It's the 2 that's the n minus 2.
There's a 2 in the denominator, then n minus 2.
2 to the n minus
4 to the n minus 2 times 4 to the 1/2.
Is going to be 4 to the n minus 3/2. You add exponents when you multiply powers.
There's another.
Oh, I didn't. All right, I didn't do what I meant. Sorry, I'm wrong. That's what I meant to do.
That's right.
4 to the a times b is 4 to the a to the b. That's what I meant to do. I need the high school practice. Sorry. If you have two numbers up in an exponent, you can do this. They mean the same thing. So I took the half out, and I left the n minus 2 up there. And this is a trick, even though I did it wrong 2 seconds ago. This is the right way to do it. And this is a trick which comes up a lot in simplifying complexity formulas. What's 4 to the 1/2? It's 2. And that's 2 to the n minus 2. That is right. And we've got another 2 here.
Those 2 to the n minus 1.
So t of n equals 2 to the n minus 1 plus, now we got to work with this piece. Ugh. But this piece isn't so bad. Let's make it 2/3. So I'll pull the third out this way. And inside, I have this. What does this turn out to be? We just did this. 2 to the n minus 2. So here's what I get. And we're still going to work a little bit more with this. 2/3, 2 to the n minus 2 minus 1. Can I do a little bit more? What if I put, I could run the 2 through to make this the same as the 2 to the n minus 1. So I get 2 to the n minus 1 plus, what? 2 to the n minus 1 over 3 minus 2/3. Everybody check me. This is just where I'm going to make a dumb mistake. Did I do everything okay so far? Yes, okay so far. Almost done. Two to the n minus 1 plus 2 to the n minus 1 over 3 is how many 2 to the n minus 1s? 4/3. 4/3, 2 to the n minus 1 minus 2/3. Now I can make this a little better. I know, it's been going too slow here. Too fast here. I can put another 2 in here. Two-thirds, 2 to the n minus 2/3. Okay, I just pulled one of those 2's, threw it back in there. And now I got the simplest way that I can think of writing this. This is what I have in my notes that I handed out. 2/3, 2 to the n minus 1. 6 rings. 2 to the 6 is 64. 64 minus 1 is 63. 63 divided by 3 is 21. 21 times 2 is 42. 42 slide moves to take this ring off. 8, it's going to be bigger. 10 is going to be even bigger. My friend bought these puzzles for his class, and he bought 10 ring puzzles. Yikes. All right, I have more stuff to do, but I'm not going to do the odd case. I'm going to leave the odd case for you to practice. But I'll tell you what you get. You get 1/3, 2 to the n plus 1 minus 1. It'll be good practice to do the odd case. So I'll just write up on the board what the answer is.
The numbers
Here you go. Here you go.
were 1, 2, 5, 7, 21, 42. If you write these as binary digits, it's 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. You're shifting it over and either adding a 0 or a 1 at the end. You're going to have all of your answers, and you're going to have the recursion, the basic recursion that you had to prove very simply from this. This is 1, this is 2, this is 5, this is 10, this is 21. And you know exactly what the next number is going to be.
What's the formula of these two?
I'm sorry?
What's the formula of it?
You can't do the formula any better than we did before.
Right, you can work out formulas, but this instantly gives you the numbers. And since the ones are appearing every other step, you're going to get the 1 plus 4 plus 4 squared plus 4 2. But this instantly gives you what the numbers are.
Sam's right, and what's more, this is a classic example of two ways of looking at the same thing. Sometimes when you try to come up with a formula to express something, you can do it, but you get this big ugly thing when a more natural way to express it is just a parent looking at it in a different way. And this is a good example of that, where you just get binary numbers with alternating zeros and ones. And you'll see things like this come up again and again.
What numbers are?
This shows you the numbers of, if you want to know how many steps it takes to solve a puzzle with n rings, just take a binary number of length n and alternate the bits, 1, 0, 1, 0, 1, 0.
Oh, right.
And then convert that to binary. Yeah.
So is the connection with this artifact of base 2 like innate in?
Yes, because you either double, which means shift over and add a 0, or you double and add 1, which means shift over and add a 1.
Right.
Except with this, we would still have to prove that is true.
I don't think it would affect anything we did. We'd still have to do everything we did to actually get a formula. But what Sam's noticing is that you could write a different program to do this. One that just gives you the answer by generating the binary number of length n and then doing 2 to the n plus. It is a different way to look at it. Pizza. All right. These represent binary numbers. 0, 0, 0, 0, 0, 0, 1 is 1, 0, 1, 2, 3, 4, 5, 6, 7. I just wrote them around. Now it does. All right. And you're playing a game with some kid. Okay, either your own kid or you're a camp counselor or who knows what. You spin this dial, boom, boom, boom. It tells you how many things to move. All right. These kind of spinner things come up not just in games, but in all sorts of mechanical contraptions, and you need to be able to see where it lies, what number it's over. It's fine. What if you wanted to build something like this electronically? This is where gray codes originally came from. I know you don't know what they are yet, but you'll find out what they are in a second. If the spinner is lying over this region, it's pretty clear that the number is 7. But when the spinner gets close to the edge, it's not really clear. And you play these games, there's a big argument whether you should spin again or whether, and people bang down, that's a tie. No, it's not. It's on this blah, blah, blah. So, but a machine that's supposed to figure out which side it's on has the same trouble. You have to build a machine that's going to do it. And sometimes it's just too close to take the pickup. So here's how somebody builds a machine like this. They have a binary sensor that sits here in this circle. Okay, and basically, it's supposed to see whether there's something on top there. And then there's a sensor for the next concentric circle, and a sensor for the next concentric circle. And if these all things light up 1, then the number's 7. And if these light up, then the number's 0. But here's the thing. What happens if it's right on the line, so that the sensors can't tell whether it's 0 or 1 here? What kind of numbers could show up? Any numbers. Anything. This could be a 0, 1, this could be a 0, 1, or this could be a 0, 1. So any number might show up. But on the display, it would say anything from 0, 1, 2, 3, 4, 5, 6, 7 randomly, depending on which sensor actually got blinked and the details of the electronics. So you want to design something like this so that when you're on the line and it doesn't know which way it is, you either get the left or the right. But that's the only two choices. And the way to do that is to order these binary bits in such a way such that any two adjacent pieces of pizza have the same 2 out of 3 binary bits, and only one differs. So if there's ever an issue, that's the only one it could be an issue on, and whichever one it says will just give you the left or right. So let me show you an example of this. The what? This arrow?
Any other arrow would work, but that one probably wouldn't work.
What do you mean wouldn't work?
The design of this makes it so that all 3 bits get
All
toggled.
3 bits get toggled when you go from there to there, rather than 1 bit.
Well, no, this is terrible. This is no good. Oh, this is bad, bad, bad.
You want something that looks more like your Chinese ring puzzle, in terms of steps.
Right, right. So let's actually write it down. This is wrong. This won't work. You can't do it in order, but this does work. 0, 0, 0, 0, 0, 1, 0, did I do this right? Sorry, 0, 0, 1, 0, 1, 1, 0, 1, 0, good. 0, 1, 1. Uh-oh. Here's how I'll do it. Let's pretend we got a 3-ring Chinese puzzle. Okay? What's the next step from 0, 0, 0? 0, 0, 1. What's the next step after this? 0. What's the next step after this? No. What's the next step after this?
0, 1, 0.
Next step? 1, 1, 0. 1, 1. 1, 0, 1. 1, 0, 0. Am I back? Is the next one 0, 0, 0? That's the sequence I want to use. And you'll see why in a second. Pizza. 0, 0, 0. 0, 0, 1. 0, 1, 1. 0, 1, 0. 1, 1, 0. 1, 1, 1. 1, 0, 1. 1, 0, 0. If you look at this spinner situation, anything that lines up on a line, if it can't tell in the second or third ring what's going on, they're both 0, so who cares? It's not going to have any trouble. The only place it's going to have trouble is in 1 bit, and whichever one it picks is either this or this one. This sequence of numbers guarantees that this machine is always going to break a tie on one side or the other that's really there, instead of coming up with bizarre numbers that couldn't possibly be there. And this sequence is exactly the same as a Chinese ring sequence that we did before. And this sequence is called a gray code. A gray code is defined to be a sequence of binary numbers where each successive number differs by exactly 1 bit, and the last one differs by the first by exactly 1 bit. So it cycles around. That's the definition. There's a lot of different gray codes. The Chinese ring one is only one of them. We could come up with a different sequence that would come back up here and be okay. If any of you are wondering whether that's possible, it is possible. But we kind of make a standard canonical gray code to be the Chinese ring one. And this is it. And I want to show you where this comes from in a more mathematical way. Let me show you the official inductive definition. This gets back to mathematical induction of how you construct gray codes. Here it is. Gray codes of size 1 are simple. 0, 1. Okay? They differ by 1 bit, and the last one differs by the first by 1 bit. The way to construct a new gray code of size 2 is to write the old gray codes down inductively, the last step, and write them down again in reverse. Put zeros in front of the first pair and ones in front of the next pair. That's the gray code for 2 bits. The gray code for 3 bits is defined the same way. It's an inductive definition. Write the 2 case down, write the 2 case down in reverse, put zeros in front of the top half and ones in front of the second half.
What are gray codes used for?
And other stuff. Wheel of. Here's the 3. Oh, look, we had it on the board already. This inductive definition builds the exact same thing as your Chinese rings puzzle. It builds the exact same thing as what we did here on the pizza store.
I'm lost as to why we would need the pizza store. What practical?
Oh, so that if you have some machine like this that needs to...
There's only one position that's funny.
Right, if there's one position that's funny, that means that when you're on a line, whichever one of these bits it decides on, it will always represent a number on this side or a number on this side. If there were 2 bits that differed here, then you could get, like if this were all 3 zeros and this were all 3 ones, then the display might say 101, and that would be someplace way on the other side. So you'd think the thing was broken, and you'd be right. So this way, if it's on the line and it can't tell, you're guaranteed to be on either side. So you want them to differ by 1 bit as you go around.
I understand that.
Okay.
When would I find that in real life? When would I find that problem?
Anytime you're building a machine like this, I suppose, or whenever you need it.
Sorry. I'm sorry, I am.
You're asking a question I don't really know the answer to. Yeah. Baruch, sorry?
The question was where you use it.
When would you use it?
Well, you could use it in digital coding, for example, to minimize the effect of a single bit error.
Oh, good idea. Right. That's a good idea. Yes.
I have a question. The distance would be for the number of steps to solve the ring would be the steps you have to take from the 111 to the 000.
Exactly.
Now, if you look at that, it's not symmetric.
Not at all.
If you look at that, so does it mean if I take the shorter path, that suggests that there is a quicker solution for it?
You mean this way?
Yeah, exactly. Why?
It depends on your initial state.
You could you only move.
No, because instead of going this way, why don't I just go backwards this way?
Does that suggest you have a faster?
Can you go from 000 to 100?
No, from 11 to 00 the other way.
Yeah, I understand.
If you look at the ring,
Right. Right.
Taking it off.
Right. Baruch asked a really good question about the particular Chinese ring. The Chinese ring thing does break down in one place, in that it isn't, well, it's not cyclical. You can go in this direction and in this direction and back to here. You can go from here to here, and in fact, you can go forward to here. But when you get to here, you can't go to here and you can't go to here. In the Chinese ring thing, these two do not connect.
it's not circular.
Right. In the Chinese ring thing, these two don't connect.
One is straight line.
100 is about the worst thing you can do in the Chinese ring puzzle. If you get everything off except the last one, and you hand it to somebody, you go, look how good I'm doing, they just smile. Okay? This looks like you've made progress, but you haven't made progress. This is the worst thing you can do. This means the hardest one is still on, all the others are off, and you cannot make the next move back to here.
Now, what,
So the actual Chinese ring,
Are not perfectly equivalent.
they're not perfectly equivalent. That's true. That's true. Absolutely right. Absolutely right.
So we're using the
Sorry, Rob, yeah.
Does the asymmetry exists in this because of the fact that we have to shuttle back and forth to get the hardest one off. The sequence of all possible on-off combinations. It's only asymmetrical if you gloss the process of removing the hardest ring, right? No?
No, it's really asymmetrical in the sense that this move cannot get to this move, and this move cannot get to this move.
Wrapped around.
Which I think is what you're
saying.
Right.
Because you got-
Yes, I understand. Yes, that's a way of looking at it,
You
absolutely.
think about progress as step by step towards your goal without thinking about the in-between steps, then it looks like you have unnecessary possibility.
Right, that's a fine way to look at it, yes. Chris, you had a question? Yeah.
When you're actually using the Chinese ring solution to get a gray code,
Yes.
what someone asked this earlier, but the goal you set for yourself is to get from zeros to the worst possible state, from zeros to 1.
From zeros to 111 is the real goal. This is what you want to do in the gray code in the Chinese ring problem.
Wait.
In the Chinese ring problem, you want to go from here to here.
Yeah. For in the Chinese ring puzzle, but
Right.
to generate the complete set of gray codes for length and
Right.
digits, how would you state that? The Chinese ring from all off to 1000.
Oh, you could state it that way. The way you state it is the way I stated it before. You take the gray code for the n-1 case. You take the reverse gray code. You write zeros in front of the first. If you want to say it in front of the Chinese rings.
Yeah, if you want to use the Chinese ring because you know this algorithm
To generate gray codes, then at this point you just keep going forward. You can keep going. When you have it all on, you can go forward in this direction even though it's bad progress.
Okay, so it's keep going forward.
Keep going forward until you are stuck, until you have to back up. Right? So it really is a line. It's not a cycle. There's two ends, and these are the endpoints. That's what Baruch was saying, and I really should mention that and distinguish it from the gray codes, which cycle. In the Chinese ring puzzle, there is no cycle at the end. You could probably build the puzzle so it would cycle, but then it'd be a completely trivial puzzle. The real thing that makes this a puzzle is that you cut the link between the top and the bottom. One last thing before I quit today. You should also notice the symmetry. Did you notice how you build these gray codes? You take the previous one, you reverse the next one, and then you double it. That's very much like the recursion we did, right? We did the n-2 problem. We reversed the process. We put them together. So that's not an accident either. You have to formalize what that really means. But there's a lot going on here. There's a lot of stuff going on with gray codes. I ask you to discover a lot of it and prove a lot of it on the problem set. Some of it's going to be straightforward. Some of it's not going to be straightforward. Ask me if you have questions on it. Last thing, today in recitation, Tara is going to explain the connection between these things and other graphs, a graph called a hypercube. And she's going to talk about Hamiltonian circuits on a hypercube, and it corresponds a lot to this. So that's coming up this afternoon.